As we've learned, a random variable is a numerical outcome of an experiment. We've also learned that a random variable and how it varies from trial to trial can be captured by a probability model. In this video, we'll learn about a common probability model, so common that it has its own name, the binomial. Take, for example, the common coin flipping scenario. Suppose we flip a coin 3 times and record x, the number of heads. In this case, x is discrete and can be described by the probability mass function here. As usual, this PMF describes the possible outcomes of x, 0, 1, 2, or 3, and their relative plausibilities. For example, we observe 0 heads with probability 1/8. That is, in the 8 equally plausible outcomes here, only 1 has 0 heads. Similarly, the probability that we observe 1 head is 3/8. This simple experiment has some special features. First, note that we have 3 fixed trials. Fixed meaning that we flip the coin 3 times every time we do this experiment. Second, each trial has a binary outcome. Specifically, in this case, we can either observe a head or tail. There are 2 possibilities. Finally, in coin flipping, each trial, or flip, is independent. That is, the outcome of any one coin flip doesn't tell us anything about another. Further, each of these flips or trials has the same probability of success. Here, success means observing a heads. In this case, there's a probability of 1/2 of observing heads in each flip. The coin flip experiment here is a simple example of a binomial framework. In general, the binomial framework has 3 properties. First, we repeat an experiment for some fixed number of trials n, where n can be 1, 2, 3, and so on. Second, each trial has a binary outcome, success or failure. And these success and failure are defined by the context. For example, our binary outcomes might be heads or tails, yes or no, pass or fail, and so on. Finally, each trial is independent of the others, and each trial has the same probability of success, p. Now notice then that the binomial framework is defined by the number of trials n and the probability of success, p. These quantities are known as the parameters of the model. Next, within the binomial framework, suppose we're interested in x, the number of successes in these n trials, where x can take on integers from 0 up to n. That is, in n trials we might observe 0 successes, 1 success, on up to n of n successes. Then this discrete random variable x has a binomial model with parameters n and p. In mathematical notation, x is modeled by a binomial with parameters n trials and probability of success, p. Now consider the following scenarios. In each case, ask whether the given random variable x is binomial. First, suppose x is the number of heads in 10 coin flips. This is very similar to the 3 coin flip example, except now we have 10 fixed trials, each trial having a binary outcome, heads or tails, and each trial or flip being independent of the others with an equal 1/2 probability of success. Thus, x satisfies the binomial framework with n equals 10 trials and a probability of success p equals 1/2. That is, x is binomial. Consider the second scenario, where x is the number of flips until we get our first heads. In this case, we might get our first head on the first coin flip, or on the second, or on the third, or on the fourth, and so on. Technically then, there's no upper bound to when we get our first heads, thus we don't know how many times we'll have to flip the coin. In this case, the number of trials in this experiment is not fixed, thus x, the number of flips until we get our first head, is not binomial. Finally, suppose we have a bag with 10 M&Ms, 6 blue and 4 green. Then suppose that I pick and eat 3 of these M&Ms and let x be the number of these that are blue. Now in this case, we do have a fixed number of trials, 3. I take and eat 3 M&Ms. The outcomes of these trials are also binary. I can either eat a blue or a green M&M. However, these trials are not independent, thus x is not binomial. Intuitively, the probability of getting a blue M&M changes depending upon the colors of the M&Ms I've already eaten. For example, suppose that my first M&M is blue, the probability of which is 6 out of 10. After eating that blue M&M, we're now left with 5 blue M&Ms and 4 green. Thus, the probability that my next M&M will also be blue is thus 5 out of 9, or a quantity that's different than 6 out of 10. Now that we have a sense for how the binomial variable works, let's formalize the model by its probability mass function. The goal here is to describe the possible values that x can take, along with the relative plausibility of these values. For any binomial variable x with n trials and probability of success p, we can write the PMF of x as follows. The probability that x is equal to some outcome little x, for any little x from 0, 1 on up to n, is equal to n choose x times p to the x power times 1 minus p to the n minus x. We won't go through and prove every detail of this result or formula here, but we can build some intuition for where it comes from. First, n choose x is the total number of ways that we can arrange x successes among n trials. That is the number of ways that we might observe x successes in the first place. The remainder of the formula specifies the probability of any one of these arrangements. For example, we have x successes, each with probability p. Thus, the total probability of these successes is p to the x. And if we have n trials and x successes, that means we have n minus x failures, each occurring with probability 1 minus p. Thus, our failures have a total probability of 1 minus p to the n minus x. Finally, let's apply this result in an example. Suppose you learn a new joke, and that there's a 20% chance that a given person will laugh at this joke. Then suppose that you tell the joke to 5 people, and let x be the number that laugh. Our goal here is to specify the model and PMF of x. In this case, we have 5 fixed trials, each having a binary outcome, the person laughs or they don't, and we can assume that each person laughs independently of the others. In other words, x is indeed binomial with parameters n equals 5 and p equals 0.2. Thus, we can plug these parameters into the general binomial PMF here to get the PMF for our variable x. The result, when we plug in n equals 5 and p equals 0.2, is this. 5 choose x times 0.2 to the x times 0.8 to the 5 minus x for any number of successes x from 0, 1 on up to 5. We can now apply this result to learn about x. First, what's the probability that only one of the 5 people laugh at your joke? To calculate this probability, we can evaluate this PMF that we just derived on the previous slide. We can evaluate it at x equals 1. That is, the probability that only one person laughs at the joke is 5 choose 1 times 0.2 to the first power times 0.8 to the 5 minus 1. And doing some math gives us our final result. There's a relatively high 40.96% chance that only one of the 5 people will laugh. We can similarly calculate the probability of any number of people laughing at the joke. This gives us an overall picture of the PMF of x, shown here. Comparatively, notice that it's most likely that one person laughs, with a probability near 0.41, as we just calculated on the previous slide. It's also relatively likely that nobody will laugh, that is, that x equals 0. At the opposite end, it's nearly impossible, with the probability near 0, that all 5 of 5 people will laugh.